Okay, so I am ready to answer questions. It can be over the relay, which you guys have just turned in, or it can be over pretty much anything else, the homework that's due today or stuff from earlier in the semester. The folks who turned in their relays more than 20 minutes ago, I've already graded them, so you might want to go back and look at the scores. I did not mark mistakes in general. I sometimes made some comments in the comments window, but since the solutions are now available on Blackboard, you can go back in and look at my solutions. With only one exception, let's see, no, he's not in the room right now. I saw one student did one of the problems in a more efficient way than I did. But for the most part, my solutions are I'm not going to say optimal, but they're pretty good. So in particular, on the problem where you have to calculate torsion, it's way, way better to go ahead and substitute in the value of t before you do all the cross products and products and stuff. If you do all the algebra with the t's in there, that just opens you up to more places where you can make mistakes. So let me turn it over to you guys. What would you like us to talk about for the next hour and 15 or so?
For 1B, can you do the vector version, I guess, that I didn't do? I know you had
That's
to.
right. You were not the only
You
one.
can.
Somebody else in the room may have done the same thing. So on problem 1B, where I'm asking for the distance between a point and a plane, a couple folks found a formula probably in the book which calculates that distance, but my goal with that one was just to see you use vector projections and stuff. So let me tell you the way that I prefer to see this on the test. So we want the distance from the point 7, 12, -10, and the plane 2x plus 5y minus z equals -6. So let me draw a picture of what the method is, and then let's do the actual calculation. So here's our plane. Here's our point P. Looking at the equation for the plane, I can find a normal vector to the plane. In fact, it's easy to see. The normal vector is gotten by taking the coefficients of x, y, and z. So let's just go ahead and observe that the normal vector is 2, 5, -1. I can also find some point in the plane Q just by picking any point Q which satisfies this equation. So one good way of doing that is by setting two of the coordinates equal to 0 and solving for the third. So for example, if I set y and z equal to 0, then I would have 2x equals -6, so x would be -3. So -3, 0, 0 is an example of a point in the plane. If I then form the vector from Q to P, I can project QP onto N, and that length will be the distance from the point to the plane. So the distance from the point to the plane is equal to the length of the projection of QP onto N. And the length of the projection of QP onto N is equal to QP dotted with N over the length of N. So let's use the P and the Q to form QP. QP is P minus Q, which is 7 minus -3, or 10, 12 minus 0, and -10 minus 0. And then QP dotted with N over the length of N will be, here's QP, here's n. So it'll be 20 plus 60 minus a negative 10 over the length of n, which is the square root of 4 plus 25 plus 1. That gives me 90 over the square root of 30. And if I multiply top and bottom by square root of 30, I have 90 square root of 30 over 30, or 3 square root of 30.
Professor,
Yes, sir.
on mine, you did comment that you'd like to see a few more steps than what I showed on this particular one. And I think that
No,
what you just,
I think I intended to make that comment on a different one.
oh, I was like, this is the same number of steps.
Nope, I meant to say that on problem 2b because I wanted to see you dotting something with v over its length,
Yeah.
and I just didn't. That step seemed to be skipped. I didn't see v. I didn't see you calculate the length of v or any of that other stuff. You probably did it in your head, but
I did.
it'd just be nice to see that step.
Okay.
Yeah, if I said that for 1b, I made a mistake. I meant to say that for 2b, Jason. So that's the way I'd to see 1b. Somebody else might have been Kevin. Calculated the distance another way I showed you, which is also kind of nice. Another way of doing it is you find your normal vector the same way I just did. Here's your point P. By taking P plus T times N, that's going to give you the line through P, which is parallel to N. And then you can intersect that line with the plane. So you take the x coordinate for the line, you plug it into the x coordinate for the plane, and so forth. That gives you an equation involving t's. So you solve for t, and you plug that back in here, and that will give you this point r in the plane, which is actually the closest point. And then the distance is equal to the magnitude of vector rp. I'm not 100% sure that was Kevin, but that feels right. At least one person did the problem that way, and that's a great way of doing it. One of the advantages of that is it actually finds the closest point in the plane. The method that we just used indirectly finds the distance, but it doesn't find the point which is the closest. While we're talking about the in-class review, since that's the only thing I've got for you in terms of a final exam review, feel free to ask questions even on the problems that you did not turn in, because it's a good idea to practice everything on here.
I feel like the angle one, the first one.
Yeah, this is one where some folks did this a little inefficiently, and let me tell you what I mean by that. This is one of the reasons I recommend that you guys look at my solutions. So sigma t is t cosine t and t sine t. And I want to find the angle between the velocity and acceleration vectors at a particular time. So the velocity, sigma prime of t, let's take that derivative. It'll be cosine t minus t sine t, and sine t plus t cosine t. And the acceleration is given by the second derivative. So that'll be negative sine t minus another sine t minus t cosine t. And for this component, cosine t plus another cosine t minus t sine t. So that's negative 2 sine t minus t cosine t and 2 cosine t minus t sine t. Now we know that to find the angle between two vectors, that cosine of theta is going to be v dotted with a over the length of v times the length of a. So an inefficient way to do this would be to dot together v and a using all of these t's. Hope that you do all your algebra right, and then plug in t equals pi. What's more efficient is to go ahead and plug in pi now before you take all those dot products and magnitudes. So notice that the velocity at time pi is going to be sigma prime of pi, and let's just plug pi in. We'll have cosine pi minus pi sine pi, and sine pi plus pi cosine of pi. Now, sine of pi is 0 and cosine pi is negative 1. So this is negative 1 minus 0 and 0 plus pi times negative 1. So negative 1, negative pi. And the acceleration vector at time pi is sigma double prime of pi, which will be negative 2 sine pi minus pi cosine pi, and 2 cosine pi minus pi sine pi. Sine pi is 0, and cosine pi is negative 1. So I'm getting positive pi and 2. So v dotted with a is negative pi minus 2 pi. So it looks like my numerator is, wait a minute, are my signs correct? Oh, cosine of pi is negative 1. So this is a negative 2 right here. So that's negative pi plus 2 pi. My numerator is pi. Magnitude of v is the square root of 1 squared plus pi squared. And the magnitude of a is the square root of pi squared plus negative 2 squared. So pi over the square root of pi squared plus 1 times the square root of pi squared plus 4. And my angle theta, of course, will be the inverse cosine of that. Making sure that you're in degree measure if you're trying to get degrees. And I get about 75.2. I don't remember whether anybody in the room did all the dot products using the t's, but even if you did, you should get the same answer when you finally plug in t equals pi. And a similar note goes for 2a, where you're calculating correlation. I would go ahead and calculate sigma prime, sigma double prime, and sigma triple prime, but then I would plug in t equals 1 before doing all the rest of the vector algebra. Just flipping over to see who else turned stuff in. Carmela, I have the feeling that I already graded yours, so you might have had a chance to look at it. Gabriel and Olivia, I see that you turned yours in, but I haven't looked at it yet. But if there are any questions, I can definitely look at them now and give you feedback on them. And you're definitely not restricted to just asking questions about the review. If you have questions about the homework that's due tonight, I can do that too. 1C, Olivia? You bet. In fact, that's a really great one to ask because it's one of my favorite kinds of problems. It has lots of good kind of basic vector arithmetic, but it's kind of a good way to check on the basics. So let's look at 1C. So I give you 3 points, and I ask you to find an equation for the plane that contains them. So here's one basic thing that you need to know when you're writing the equation for a plane. The 2 ingredients that you need are a point in the plane. I'm going to call it P. And you need a vector n, which is perpendicular to the plane. Let's say that the vector n has components a, b, and c. And let's say that P has coordinates x naught, y naught, and z naught. Now, the formula that I'm going to develop is one that you may be familiar with. And that's that the equation for the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. But I'm going to take just a moment to remind you why that's true. If we pick any other point, x, y, z in the plane, and we form the vector from P to that point, then those 2 vectors are perpendicular. So let me call this point over here S. So I know that n dotted with S has got to equal 0. If 2 vectors are perpendicular, their dot product is 0. So vector n, oh sorry, not vector S here, vector PS, the vector from P to S. Sorry about that. Vector n was A, B, C. And vector PS you can find by taking S minus P. So that would be x minus x naught, y minus y naught, and z minus z naught. And when you carry out the dot product, you have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So I can put all of this stuff in a thought bubble. You don't need to write this down as part of the solution. I was just trying to remind you why this formula is true. So we certainly have a point in the plane. We've got a point P that we can use. We can use 2, 1, negative 1. But I need a normal vector. And one way I can get a normal vector to a plane is by taking the cross product of 2 vectors that live in the plane. Remember, if you take the cross product of any 2 vectors, then it'll give you a vector which is perpendicular to both of them. So if I name my points P, Q, and R, as they were in the problem, the vectors I can use are the vector PQ and the vector PR. So for my normal vector n, I can take PQ and cross it with PR. So PQ is Q minus P, which is -2, -3, and +1. PR is R minus P, which is -1, -2, and 3. And then I can take their cross product by forming the matrix I, J, K, along with those vectors, and then doing the cross product. So my normal vector, which is PQ crossed with PR, in my first component, I have -9 plus 2. In my second component, I have -1 plus 6. And in the third component, I have 4 minus 3. So I appear to be getting -7, +5, and +1. And at this point, I can use this normal vector as my ABC. And I could use any of these points. So I could use P, but I think I'll take advantage and use Q since it's got some zeros in it to make my calculations easier. So I have -7 times x minus 0 plus 5 times y minus -2 plus 1 times z minus 0 equals 0. So -7x plus 5y minus, 5y plus 10 plus z equals 0. So -7x plus 5y plus z equals -10. And I don't really like starting the equation for playing with a negative number, so I might multiply through by -1. It's correct both ways, but to me it looks better to have my leading coefficient positive. So 7x minus 5y minus z equals 10. And one of the really nice things about problems like this is you can check it and be 100% sure of your answer if all 3 points satisfy that equation. So if you just take P, Q, and R and substitute each of those in, then you ought to get 10 for all 3. And if you do get 10 for all 3, you know you've done it. I think another person or two might have popped in while I was doing that problem. During this section, I'll be glad to answer questions over the review sheet or the homework or pretty much anything else. Graded homework 9? Sure, let me see if I can pull that up. Oh, that was the one with the cylindrical coordinate, calculating the volume of a cylinder, right? I'll be glad to do that. For the folks who are in the other class, not the honors class, one of the problems that they had to do was to find the volume of a cylinder with height h. So this distance is h, and radius r. And they had to do it using rectangular coordinates, cylindrical coordinates, and spherical coordinates. And they should, of course, got the same answer all 3 times. The volume should come out to equal pi r squared h. So even though that was an assignment for you, it's a really good problem for practicing finding or using rectangular, cylindrical, and spherical coordinates. Okay, so Gabriel, what part of that problem did you want us to look at? Was it the spherical coordinates? That's kind of the hardest part. Okay, I guessed it. So let's do that. Let's put this cylinder in the XYZ plane. So we'll make the z-axis go up. Put my x-axis this way. y-axis this way. Notice that the top plane has equation z equals h. The bottom plane is z equals 0. And this cylindrical wall has equation x squared plus y squared equals r squared. So before we do a lot of calculations, let's just translate those three equations into spherical coordinates. So x, y, and z are row, 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 working from bottom to top. Cosine phi, sine phi, sine phi, cosine theta, and sine theta. And dv is rho squared sine phi, d rho, d phi, d theta. So you guys all know that that's stuff that you should have memorized for the. So in particular, you do not have to use the Jacobian to calculate dv. I'm assuming that you guys have that memorized. So let's take them one at a time. The top of this solid is z equals h, which is the same as rho cosine phi equals h. So rho is h over cosine phi. In other words, it's h secant phi. I'm going to do the bottom up here. The bottom, z equals 0. So rho cosine phi equals 0. So cosine phi equals 0. And that happens at phi equals pi over 2. And in retrospect, we realize that that's true, that if we look at all the points where phi is pi over 2, then that's exactly the xy plane. And last, for the cylindrical wall, we have x squared plus y squared equals r squared, which is the same as rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals r squared. Since sine squared plus cosine squared is 1, we get rho squared sine squared phi equals r squared. So rho sine phi is r. So if I divide both sides by sine phi, rho is r over sine phi, which is r cosecant phi. All right. So now what I'd like to do is take, fix theta for the moment and just take a cross section for that particular theta. So let's say that I'm fixing, oh, that's not a good angle. Let's say that I'm fixing this theta. So this angle right here. Then notice that that gives me a rectangle and this plane contains the z-axis. So let me turn that rectangle so that we can look at it a little bit better. Going out in this direction, I'm increasing r, so I'm going to call this the r-axis. And this is z. This top line is part of the plane z equals h. So that top line is the same as rho equals h secant phi. And this part, the vertical line, is part of the cylindrical wall. And that's the same as rho equals r cosecant phi. So when I fixed a particular theta, notice that r is going to be coming out of the origin. Let me change colors here. It's going to come out of the origin, and then it's going to cross either this top plane, if the angle phi is fairly small, or if the angle is bigger, then it's going to cross the vertical wall. So when phi is bigger, rho is going to go from the origin out to the wall, rho equals r cosecant phi. And somewhere in the middle, right here, is going to be the angle which separates the two. So if I slowly move theta starting at 0 and going to 2 pi, when theta equals 0, then I'm going to be exiting right here at h. Then I'm going to continue out like this. So rho is going from 0 to h secant phi all the way here. Then I get to that special angle. And once I go past that, then rho is going from 0 to r cosecant phi. So I'm going to have to do two different integrals and add them together. Let me see how much of the integral I can write down where just for the moment, I'm going to call this mystery angle question mark. So the volume is the triple integral of dv. Let's split this up into two separate angles, or two separate integrals. dv is rho squared sine phi d rho d phi d theta. Rho squared sine phi d rho d phi d theta. On both parts, theta is going from 0 to 2 pi. Now on the top part, the green part, phi is starting at 0 and it's stopping at the mystery angle. And on that portion, we start out at rho equals 0 and we stop at rho equals h secant phi. In the second integral, the part that I've shaded in purple, that starts when phi is at the mystery angle question mark, and it stops when I get to phi equals pi over 2. Remember, that's the xy plane. And on that section, I go from rho equals 0 to rho equals r cosecant phi when I hit the vertical wall. So notice that the only part that I don't have is the mystery angle phi. So let's do a quick calculation to figure out what that is. Notice that this point, which I'm coloring in black, is the intersection of the top plane and the vertical wall. So let's set their equations equal to each other. H secant phi equals r cosecant phi. In other words, h over cosine phi is equal to r over sine phi. So if I multiply both sides by sine phi and divide both sides by h, I get that tangent of phi is equal to r over h. So phi is the inverse tangent of r over h. So r tangent of r over h is the angle that needs to be filled in for the question mark in each of those two integrals. And then, of course, Gabriel, you'd have to go through and finish carrying out the integration. One of them, I don't remember which, one of them ends up being a third pi r squared h, and the other one is 2/3 pi r squared h. So when you add them together, you get pi r squared h. I think they are in that order, but they could be reversed. So for the guys that are in the 1145 class, that was not a problem that you were assigned. Does anybody have a question about this one? Olivia, I don't remember whether you finished this one in the homework you turned in. Jason, you did, I know. Okay, what else would you guys like to look at?
Professor, can you go back to the first problem and explain the negative sign?
Which first problem? Problem 1A off the relay?
The problem number 5 in the homework. Bookwork. The one that you did earlier, but
when I was
wasn't
talking to
here.
Diego?
Yes, I think.
Sure. I think that the question that we're struggling with a little bit is the idea of an outward pointing normal. So what I'd like, before we do that particular problem, I want to make an analogy, see if it rings true to anybody. If I have a solid, so I've drawn a potato for you here, I want you to imagine sticking a toothpick into that potato so that it's halfway pointing inward and halfway pointing out. So the part that I've drawn with the dashed line is in the flesh of the potato, and the part that out here that I've drawn with a solid line is pointing into the air. The outward pointing normal vector is the one which is pointing into the air. So the part in here is surrounded with potato, and the part out here is surrounded with air. So in the problem that Diego was asking, which I think everybody should be working on because everybody had the same problem assigned in the bookwork. We had a triangular pyramid, which was kind of sitting in the corner of a room. If I remember, the equation for this plane was x plus 2y plus z equals 6, I think. And on each of the four faces, we're going to have to identify what the outward pointing normal vector is. So if I have a point on this back wall, so I want you to imagine that being on the back left side, so that's a vertical triangle, the outward pointing normal is going to point in the direction of the negative y-axis. So the positive y-axis is this way. The part that points out into the air is going to be going in that negative y-direction. So that's like 0, negative 1, 0. Here, if I draw a normal vector, it's either going to point toward the positive or toward the negative x-axis. The outward pointing normal is going to have to point away from this triangular pyramid. So it's got to point backward along the negative x-axis. So the normal vector there has got to be going in the direction of -1, 0, 0. If I pick a point on the bottom, then my normal vectors are either going to point upward toward the positive z-axis, or they're going to point downward toward the negative z-axis. Upward would be pointing into the pyramid, so I've got to point into the air, which will be downward. So it's got to be pointing parallel to 0, 0, -1. And last, on this triangular surface here. So on the surface, x plus 2y plus z equals 6. Notice that I can get a normal vector by just taking the gradient. So 1, 2, 1 is a normal vector. So two normal vectors will be plus or minus that. Notice that the vector I want is going to be the one which is pointing out of the solid. And notice that from the way that it's tilted, that vector is going to be pointing above the horizon. So it's going to have a positive z component. So since the z component here is already positive, I'll be choosing something which is parallel to 1, 2, 1. Now, depending on your parameterization, you could end up with 2, 4, 2, but I want the one that has a positive z component.
1, 2. Never mind. I was just trying to figure out what plane it was from.
That's from the plane x plus 2y plus z equals 6. I think in the book it was 2x plus 4y plus 2z equals 12.
Yeah, so it took me longer to simplify that.
Yeah, I don't know why they left the common factor in there. That's just going to complicate the calculations. I've already forgotten who asked that question. Kevin? Somebody did. Did I answer the question about choosing the plus or minus?
Yes.
Okay, cool. Oh, trim. Okay. So one thing that Diego was a little surprised at is that from the way that he parameterized this back left plane, the cross product already gave a -1 in this spot. So in choosing the plus or minus, he ended up choosing the plus because the negative had already shown up in the cross product. So the plus or minus on the outside is not what's important. What's important is what happens when you multiply in that number, whether it gives you a positive or negative where you want it to be. That's a good thing, the cutting kind of late in the semester. So Gabriel's asking the best way to study for the final. So probably, I'm trying to think of what the most efficient way to study would be. You guys still have a lot of time, but this is probably the first or second of your finals. You probably have some others later in the week, so you're preparing for more than one thing at once. I would think about this review, the in-class relay, as kind of a diagnostic. So work all the problems, including the ones that you didn't turn in, and just take note of the ones that you're really having to look up a lot of stuff, the ones that you're not remembering how to do very well. So, for example, Olivia asked the question about the equation for the plane, problem 1C. Chances are, when we did exam 1, that's one that everybody breezed through, but over the last 12 weeks, you may have forgotten how to do it. So pay attention to which things you most need to brush up on, and then go from there. So if it's exam one stuff that you really need to brush up on, go back and hit the relay and the review sheet for exam one. If there are things on the relay that you found like super easy, then just do a brief refresher on that. But concentrate on the stuff where you see that you don't remember things as well as you used to. Another thing is, here toward the end of the semester, we've learned 3 of the Big Four theorems for the semester: the fundamental theorem of line integrals, Green's theorem, Stokes' theorem, Divergence theorem. And on each of the tests, except for the first one, or did we have the FTI already? But on most of our tests, you've had to do a problem where you calculate both sides of one of those theorems. So for a Green's theorem, you had to find the integral over the interior and the integral around the boundary and verify that they're the same. So that's not really the best way to use that theorem. When you're using Green's theorem or Divergence theorem or Stokes' theorem in another class, you're going to be using that to figure something complicated out by switching it from one side of the equation to the other. But the main reason I'm giving those to you on tests is to make sure that you can do all the basic kinds of integrals. So in terms of integration, the kinds of things I want you to make sure that you can do is, in one dimension, you need to be able to find the integral along any curve of integrals of the form f dot baby ds. You also need to be able to integrate a function multiplied by scalar ds. So the scalar version is something that you would use to find arc length or mass or center of mass. Integral over here could be used to find work or flux across a curve. This side is also the kind of integral that would show up in fundamental theorem of line integrals. Two dimensions, make sure that you can set up and do integrals in the plane. So integral of f of x and y with respect to a. And make sure that you do that in both rectangular coordinates and polar. When you have a surface in 3 dimensions, so I want you to think about this as being a surface, not a solid, so something 2-dimensional. Then you need to be able to parameterize. And as soon as you parameterize, you ought to be able to do 2 different types of integrals. So you ought to be able to find integrals where you find the flux through that surface. So that's like the kind of integral that we were just talking about in that problem 5, where you're finding f dot ds. Notice that this is capital S, and this is a double integral. And you also need to be able to find the double integral over S of just a function times scalar ds. Again, the second one is something you could use to find surface area, or you could use it to find mass or center of mass. The one on the left would be something which showed up as a flux integral. And divergence theorem is an example of when you might be finding an integral of that type. And make sure that when you parameterize, you can parameterize it using rectangular coordinates, cylindrical coordinates, and spherical coordinates. Instead of saying using, I'm going to say adapting. Because remember, when you do an integral over a surface, you're only going to have 2 parameters. And each of these systems of coordinates has 3 parameters. What you're doing is you're substituting these, whichever one you choose, into the equation for the surface, and basically eliminating one of the parameters so that you only have 2 instead of 3. And then in 3 dimensions, you have some solid in 3-dimensional space. Here, you basically just need to be able to do a triple integral over that solid. I've generally been calling these guys Q of f dv, but you need to be able to do it using rectangular, cylindrical, and spherical coordinates. If you can do all of those things, then you're not going to have to worry about Stokes' theorem or divergence theorem or any of that, because each side of the equation is going to be one of the integrals kind of on this page. One thing I'm noticing though, and I don't know whether it involves anybody in the room right now, but problem 2C on the relay asked you to find the divergence of the curl of a vector field. And there are people who did not calculate divergence of a vector field right, and they did not calculate curl right. So you must know how to find the divergence of a vector field and the curl of a vector field. So divergence I'm typically writing as del dot f, curl I'm writing del cross f. But some people are making mistakes in understanding what that notation means. So if you tried 2C and didn't get it right, make sure that you read my solutions so that you see the correct way to calculate divergence and curl. And that's most of the integration stuff, Gabriel. Remember, there's also a lot of stuff about differentiation, including solving max-min problems and stuff like that. Part 3 on the relay hits 2 of the highlights there, where you're finding absolute extrema and also finding relative extrema using the Hessian test. That's really good stuff to hit also. I just got a sound. Either that was somebody leaving or somebody has a question. I don't see a question. Maybe it was just Olivia leaving. Oh, rectangular coordinates are just x, y, z coordinates. X equals x, y equals y, z equals z. Yeah. So we still have about 17 minutes left. I will be downloading this recording and posting it to Blackboard after a while. So if you weren't here at the very beginning, then it'll be there in a couple of hours. It takes a while to process. Is there anything else, though, that you'd like us to work on, either a specific problem or just kind of general questions over something we've done over the course of the semester?
Can you just like go over coordinates, like an example of it?
Sorry,
I still have
which one?
kind of trouble. Spherical coordinates.
Sure. So one example of spherical coordinates is that calculation I did earlier with the cylinder. Let's see if we can do maybe one other example. I'm trying to think of a good one. Yeah, let's think of this. First of all, I want to draw a picture, make sure you understand what I'm trying to calculate, and then let's see if we can set it up. Let's say that we have a sphere of radius, I'm just going to make it up, radius 5. X squared plus y squared plus z squared equals 25. And we intersect that with the plane z equals 3. Then the intersection is going to be a circle. Let's say that we want to calculate the volume of this top part, which is bounded above by the sphere and below by the plane. Does the picture make sense?
Yeah, so and a question would probably like ask you like find the volume or whatever of the upper half.
Not the upper half. I'd say find the volume of the solid which is bounded above by the sphere, x squared plus y squared plus z squared equals 25, and
Okay.
below by the plane z equals 3,
Okay.
using spherical coordinates. So I could say set up and evaluate in spherical coordinates. So let's go back and review x, y, z, and dv for spherical coordinates. X is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. And dv is rho squared sine phi d rho phi d theta. Carmelo has an observation that this might be, oh yeah, so this is similar to one of the problems on the relay. Yeah, so if you didn't do that part on the relay, this might help out with at least half of it, which is actually the easy half. Oops, oops, actually 4b.
I think I did it,
Oh,
but
sorry,
it was
4b, Carmela, is actually a little bit different because you're still going to use spherical coordinates, or you may use spherical coordinates. That's the way that I did it in the solutions. But that's a double integral over the surface rather than a triple integral over the interior, over the solid. So it's related, but not exactly the same. Okay, so let's use our spherical coordinates to transform each of these two equations into spherical coordinates. So I'm not going to do the calculation again, but in spherical coordinates, x squared plus y squared plus z squared is rho squared. So if you take these equations for x, y, and z and substitute them in and use the Pythagorean theorem twice, you'll get rho squared equals 25. So rho equals 5. So the sphere is rho equals 5. And for the plane, z equals 3. That's the same as rho cosine phi equals 3. So rho equals 3 over cosine phi, which is 3 secant phi. And now let's do something similar to what I did for that cylinder example. Let's slice this solid with a plane which is coming out at an angle theta from the x-axis. So I don't know how well this is coming out, but the slice with this little piece of the solid is going to look something like this. So let me draw it out. If this is a radial line, then I'll call this the r-axis and this is the z-axis. And the piece of the solid I've got looks something like this. Where this curved part is part of the sphere, rho equals 5, and this horizontal line is part of the plane, which is rho equals 3 secant phi. And now let's start setting up the integral. So volume is the integral of dv, so I have my rho squared. And I think d rho d phi d theta is going to be fine. D rho d phi, d theta. Because the solid is symmetric around the z-axis, and you go all the way around, theta goes from 0 to 2 pi. Let's look at what rho does. Here's a radial vector coming out from the origin. That's the way rho measures. Rho measures out from the origin. Notice that it's going to enter the solid on the plane and then exit the solid on the sphere. So I'm going to enter when rho is equal to 3 secant phi. I'm going to exit when rho equals 5. And I wrote those in the phi place rather than in rho, so I need to move that over. Rho goes from 3 secant phi to 5. So let me scribble that. Now, since the rho bounds involve phi, that means that phi has to go further out. I just got a notification that my picture might be degrading. Sorry about that. Let's finish up by figuring out what the bounds on phi are. So I am going to start off with phi equals 0. So phi equals 0 is pointing straight up, and I do get part of the region there. So phi starts off at 0, and the biggest value of phi is going to be when the sphere and the plane cross. So in that earlier example, this is what I was referring to as the missed triangle phi. So let's figure out where these two guys cross. To do that, I'm going to set their two equations equal. So I have 3 secant phi equals 5. So secant phi is 5/3. I'm going to switch to cosine. Cosine phi is 3/5. So phi is the inverse cosine of 3/5. And that's going to be the upper bound for phi, the inverse cosine of over 5.
And then the max range for phi, or just in general, like the pi value, it would be going from like 0 to pi, right? It doesn't go to 2 pi?
I would never go bigger than pi for phi.
Okay.
If I were to continue the picture of the sphere, so I'm generalizing this picture. The sphere goes all the way top to bottom along the z-axis. Directly up is phi equals 0. Horizontal, the xy plane, is phi is pi over 2. And directly down is phi equals pi. So for the part that I care about in this problem, I'm starting at 0, but I have to stop over here at the inverse cosine of 3/5. So notice I'm not going all the way to pi. I'm starting at 0 and stopping here at some acute angle. But you're right, we're never going to take phi bigger than pi. Okay. And if it's above the xy plane, I'm never going to go past pi over 2. Still have a couple minutes left. I don't mind if I get a question that lasts a few extra minutes. Oh, yesterday in my Cal 1 review, I got several people said that they would appreciate an extra bit of review on Friday. So we give them from 10 to 10:30 in conference tomorrow, and I'll be glad to meet with you guys from 10:30 to 11 if anybody wants to show up. I'll be posting an announcement on Blackboard after the session's over, or maybe a little bit later this afternoon. So if you showed up and I didn't answer all your questions, or if you develop some more questions after you study tonight, just pop in between 10:30 and 11 tomorrow, and I can answer your questions then. Also, feel free to use the discussion boards if you want to ask questions there. I'm checking the discussions boards about 10 o'clock in the morning. And if I don't get to your question, one of your classmates might. And you might also want to use the discussion board to set up some review sessions, because I'm probably could be available over the weekend, so it might be your best bet to meet with some of your classmates in a study group online this weekend.
I'll probably learn that after I work the rest of these bonus items due.
That sounds like a good plan. Michael, I think that I would supplement the most recent relay with the other relays from earlier in the semester. I wouldn't necessarily delve into all the homework for the semester, but based on the results, based on what people turned in for the review, some folks are looking rusty, especially on the earliest stuff in the semester. So it might be good to go back and look at the relay or the review sheet for exam 1 or exam 2 if you think that you've forgotten some of that stuff. Also, just in general, if anybody, of course, if there was one of the tests that really hurt you more than the others, you probably want to go back and study that a little bit extra too. I am seeing good stuff on the relays. After this session's over, I'm going to try to grade everybody's who turned theirs in. Seeing Gabriel, Bryce, Olivia, and Chris Zarco one class, Mahina the other. So if you turned it in, then probably within the next hour or so, I'll have that graded. In part B on 4B on the relay. Yes, Carmela, you could even do that using rectangular coordinates, but any of those 3 coordinate systems would work. It turns out that something especially cute happens in that problem. If you use rectangular coordinates, you have some interesting cancellation, which makes it a fairly easy integral to do. But I'll tell you that when I was working out the solutions myself, my instinct was to use spherical coordinates, and it worked out great. But I wouldn't necessarily say that that turned out to be the most efficient way to do it.
Okay, well, I tried to do that, but like I did not get the right answer. And you don't have to work it out. It's just like I feel like I messed up on the on parametrizing it, I feel like. I don't know.
So if you're using spherical coordinates, then the parameterization would be pretty standard. Since it's a sphere of radius 2, you would use this set of coordinates that I've got on screen, only rho would equal 2. So the parameterization would be 2 sine phi cosine theta, 2 sine phi sine theta, and 2 cosine theta. And then you would just go through. I think that you would end up with your ds equaling 4 sine phi d rho d phi d theta.
Yeah. So if I were to use, or I did use the cylindrical, would my parametrization, I don't know how to say that word, would be x equals 2 cosine theta, y equals 2 sine theta, and z equals z? Or
no, that would not be it. Let's actually spend a moment on that because that's a good question. That would be a good thing to end the session with. Let's parameterize z equals the square root of 4 minus x squared minus y squared by adapting cylindrical coordinates. Maybe you can hear in my voice that I just got excited about the question. This is a good one. So to begin with, we're going to think of the general cylindrical coordinates, which is r cosine theta, y equals r sine theta, and z equals z. And we substitute that into the equation. So we have z equals the square root of 4 minus r squared cosine squared theta minus r squared sine squared theta, which is the same as the square root of 4 minus r squared. So So one possible parameterization would be to plug that back in. So x equals r cosine theta equals r sine theta, and z equals the square root of 4 minus r squared.
Wait, so you don't carry out like the rest of the square root of 4 minus r squared?
In what way?
Well, I ended up getting r equals 2, but I think I did it wrong. Okay.
I'm not going to insult you by saying that this is what you did, but what someone might do is say that the square root of 4 minus r squared is the same as 2 minus
Yes,
r,
that's exactly what I did.
which of course it isn't, right?
Yeah,
You
okay.
can't take the square root of a plus b and get square root of a plus square root of b. You can't distribute square roots like that.
Okay, well, that's exactly what I did. Okay. Well,
I don't think that you were the only one who actually did that. I'm pretty sure I saw somebody else do the same thing. It's a common mistake.
okay.
It's
Well,
okay.
no, thank you.
Okay, folks, any last minute question? Okay, I'm going to end the session. Let me stop the recording. And